equation motion for system only is really difficult. It's not easy, but the price we paid actually, will be really somehow become very rewarding, because in terms of numerical simulation, in terms of physical interpretation, we really gain a lot by doing this. Okay, so now let's see how to do this work. So how a combined system is a unitary operator, right? So here, I perform a measurement. So this is kind of, of course, I actually make it clear. This all quantum information in quantum information, right? We have many quantum control schemes. None of them is really universal, which means, this one is universally valid, useful, efficient. We don't have that kind of thing. Basically, we have to think of, for a given quantum system, you have to decide which one is better for your purpose, but not universally valid, or maybe theoretically valid, but not universally useful. Yes.
I have several naive questions. First one, are your rows matrices or are they numbers?
Matrices.
Okay. Second question, do your ends and this vacuum state form a complete set?
The vacuum.
Your end state and the vacuum zero
state.
Here,
right?
Yes. Do they form
this
a
one
complete set?
including vacuum. If I use bulk states,
okay.
I use a photon number, right? Vacuum, 1 photon, 2 photons, so on and so forth. Yes.
Right. So your end starts from 0.
Exactly.
Okay. Thank you.
Good.
And third question. Usually, if I have an operator sandwiched by a bra and a cat, that should give me a matrix element. But in your notation, you seem to tell us this sandwich is still a matrix.
That's a good question. Yes, that's a good question. Yeah, that's right. You have to just count the dimension, because if you think about I have an n-dimensional space, right?
Right.
So the dimension of your vector is n, and the matrix is also n. So when you have this sandwich type product, it's called mean value, right? You get a number. So the question, why we have a matrix here, operator here? Because if you count the dimension, I should make it clear. Yeah, that's a very good question. I think it clarifies something. Because you see, this U, right? This U is for total. But this N is only for the environment. So you use a subsystem vector. Total you have 100 degrees of freedom, right? But you also use the environment 80, then you still have 20 there. So that's why here, after tracing, this is called a partial trace. So after this partial trace, you still have an operator. That's a very good question. Thank you. Yes. So here you see, now my trick is here. I perform measurement on environment. I get some information, but only one shot measurement. I'm not doing somehow continuously, like a quantum feedback control. You have to, constantly monitoring, the environment. Here, I only make a one-shot measurement. Then use information here, because you see, each Kn corresponds to one particular measurement output for the environment. So, for instance, if I have performed the measurement on the environment right here, the result is M1. Okay, I know the system here, will jump to K1. If here my result outcome is M2 here, then I know, although originally before measurement that's the sum. We have if you totally have n terms, right? 100 term, whatever. If n is 100. So, but after measurement you only have one term left. Then this basically, performing a measurement, a projection of a measurement on environment, essentially collapse the system here into a particular state, described by, Kn, this sandwich structure. Because by assumption here, the K is unitary, right? Then you can perform quantum operation, reverse this one. So that's the idea, This actually was proposed by Werner. It's very clever, but it's highly efficient, because the first one, I said the efficient because we only perform one measurement. This is the one thing. The second one is we can perfectly recover the original state. So which means in principle, the fidelity is 1. Fidelity is 1. Also, this whole process is a deterministic. You really don't have something like, I have to repeat these processes many, many times. Eventually, I get something I want. You only have one system. You only have one state here, sending through the channel. Then with one state, you can recover the original state. This is called deterministic process. So here is one example. I just show you one example here. For 1 qubit, why we can do this? Naively, you can think about, I have in quantum information, people typically talk about, I have Alice ball, right? So Alice can have solve this problem. She could have a decomposition. Bob could have another one. So Alice might find, her decomposition is not unitary, but Bob found his decomposition is unitary. So because if you just blindly try to find out decomposition, of course you might not be that lucky. So your decomposition might not be unitary, but there's a relationship between them, up to a unitary transformation. So anyway, so we know, sometimes if you write down your decomposition is not unitary, but doesn't mean the channel itself doesn't, have this kind of decomposition. So you have to, to show, you have to try harder, to perform unitary transformation, just rotate the system a little bit. So here, just one example. If you use this one, this is the particular decomposition here. Of course, you see, this is the K1, right? K1 here, K1 dagger, K2 dagger. But if you look at this one, certainly this is not unitary, right? This is not unitary. This even not the invertible matrix. So this decomposition certainly is a non-RU, right? But I can, slightly make a transformation. This is a perfect, random unitary decomposition, if this one. So here you found this one, of course, I can perform measurement on the environment and recover the state. Yes?
I have a question about the first line on this slide, the first line of equations.
Okay.
Where you have rho S of t is written in 2 different ways.
Right. Right.
As a result of Krauss operators acting.
Uh-huh.
And then on the right side you have CT, and then there is this open circle symbol, which I'm not sure, acting on rho as 0.
This one, right?
I would have expected there for CT to be some kind of super operator.
Yeah, exactly.
And then if rho S of 0 is 2 by 2
this
matrix,
is this
can
is
I finish? Can I finish? If
okay.
rho S is a 2 by 2 matrix,
Uh-huh.
I would have guessed that CT would be 4 by 4 or so. We also do these things. If you have for one
This
qubit,
just the notation. Just notation, yeah. This acting as a super operator, just notation. This one represents the final state. This is the final state, right? So you by performing this one or this one, this is the final state. You work on this one, that's the final state here.
maybe
This
as long
only the
as long as
notation.
this open circle notation is
Right.
not clarified.
Right.
And basically,
right.
I don't know what it means, so I shouldn't be too definite either.
This just, you can think about this. This is kind of called the element-wise definition. So this one acting on this one, then this one acting on row 1, 1. This one acting on row 2, 2. This one
I should
row
see.
1, 2,
I should see
2, 1. Yeah.
the
This is
definition.
called the elements-wise definition. Yeah. Right. Okay. So anyway, so I show you one particular example here, right? Indeed, RU decomposition exists. Also, I should mention, in quantum information science, there's, as I said, there's many different kind of noises, right? But 2 kind of noises are extremely important. One is called dephasing. This is the pure decoherence. The other one is called amplitude noise. So this is one example, called dephasing noise. Although mathematically it's simple, but physically extremely important. So, okay. So I think I also show you, this why the kind of picture, why we can do this kind of things, So, this is the kind of final result, right? So here you see final result, of course, starting from the initial superposition here. I didn't write down, I think explicit, yeah, the precise, like the superposition, is a pure state. So, but the final state, if you look at this one, immediately, this is not pure state, right? It's a mixed state because the coherence term here and here disappear. So this one is a mixed state. Starting from a pure state, I haven't shown this is a kind of, I have this final state, but final state can be decomposed into two processes. This is one component, this is one component here. This one is another component for cross decomposition. Each one is like a pure state. So you have two branches, essentially like a quantum trajectory. I have an evolution starting from pure state to the final, the mixed state. But there's many ways to realize this. So one particular trajectory is a pure. For each of them, you can recover. But how can we get one particular trajectory? By performing measurement on the environment. One particular realization of measurement on the environment corresponds to one particular trajectory for the system. That's that's actually the physics behind this scheme. Okay, so I will go very quickly here. So what's the advantage of this RU decomposition? I already mentioned this one, right? So we relatively efficient because we only perform one measurement, and also highly efficiency. Here the fidelity, which is a measure for the the state if your operation is good or bad, worse, whatever. So you use the concept is called fidelity. If fidelity 1 means you recover the state perfectly. If fidelity 0 means you basically doing nothing. So in this scheme, the fidelity is 1, which means you can perfectly recover the original state. And you only perform one quantum measurement, and also, most importantly, the process is deterministic. But I mentioned this already, so I will go quickly. Unfortunately, this is not something widely found in quantum information science, which means for most physically interesting channels, they do not have RU decompositions. You have to somehow, how to break this limitation. So this is our work. So our work, we try to do something. The first paper is published last year. So we here in this work. So I think the idea is very clear. We try to find out try to break this limitation. So we try to use a non-RU decomposition, but can also do the same thing, which means we can use non-RU decomposition to recover original state. So this is a kind of quite interesting idea. But the question is how to implement this idea. Okay, so we can talk about n-qubit case here, n-qubit case, because Werner's original paper only dealt with 1 qubit, because he basically proposed this idea, and at that time he didn't know what's the limitation here. Maybe there's a lot of here we show explicitly how to work out the n-qubit case, also with a non-RU decomposition, because RU decomposition, as we said, is very limited. So we have to do something to how to exploit a different decomposition. So this is our idea. 1, 2 bit. Here is really the n equal 2. So I found this decomposition here. This is an explicit example here. We work out carefully. Everything here you can see we have 4 cross operators. There are RU matrices here. You see here 1, 1. You see RU basically by definition, right? The matrix has an inverse, which is just the Hermitian conjugate. Hermitian conjugate is the inverse, right? So this one of course Hermitian. That's just real matrix. So Hermitian conjugate just essentially means the KC2 square is 1. Of course, they all satisfy the same conditions, right? So they are perfect unitary matrices. So we can find out these particular examples here. So we can apply the same idea to recovering the 2 qubits case, but this is somehow is a yes.
On the, now I have to think, on the previous slide, those coefficients square root x1, x2, those are pure phases, or that is not?
Not pure phases. This essentially gives us somehow the weight. You see, when you have decomposition of k, right? So k is time dependent. So all of time dependence terms, I have to write that explicitly. But x1, x2, x3, x4, all time dependent coefficients.
Could you remind me, go back 1 or 2 slides, the definition of the RU decomposition?
Okay. Right here. This one here, RU decomposition. Each k is proportional to the yeah. Not necessarily untangled because, as I said, the item doesn't know itself, it's normalized or not. So it's just a normalized factor. So you perform quantum operation, you restore quantum state. But if you do the mathematical calculation, of course, you have to normalize your state in order to have a consistent result. Okay, so I try to do this one, I try to use non-RU decomposition. I know, for dephasing, we can find, even for the n qubits, we can find the RU, but RU sometimes, is not that convenient. Here, instead, we try to use non-RU decomposition here. So this is a work, I said, is already published here. So let's see how to do this non-RU. So I just, try to, I have this one, you see. I have 2 qubits here. Couple to, you can think about, a two-level item. Put 2 items into the cavity, right? This is the cavity mode, the cavity here, the cavity mode. So that's a light field. So you have a mutual interaction between the item, so item and the cavity. But this one, to be careful, you see here, I'm not really talking about the dissipation model. This is the dephasing case as the first one. Second one, I will talk about dissipation case. So then, I can find out the cross operators, the k operator, we call it cross operator. You have decomposition, right? So here, I can find the cross operator by 3 different, kind of observations here. That's the 3 for 2 qubits. For 2 qubits, I have a 3 cross operators. But if you look at it carefully, none of them is an RU decomposition. They are not, right? Because this one is invertible. It's not invertible. Of course, RU matrix definitely is invertible, right? Actually, more than that. You have the inverse just by performing the Hermitian conjugate. So this one is not RU, not RU. And this one, of course, is invertible. But unfortunately, the coefficient L1 here, are different from this one, right? So you can think about this one, of course, the inverse is not really just performing, not obtained by performing a Hermitian conjugate. Because this one is a real, but unfortunately, this is not. 3 matrices are not RU, but we can use this non-RU decomposition.
If I look at the definition of L1T below, then I could guess that in certain regimes L1T becomes exponentially small. Then even the leftmost matrix is invertible only in name, and it would be very unstable.
Yeah, I think I will show you. We can use some way to exploit the structure of L1, L2, L3. Yes, that's I will show you here. So here you see in this my question, of course, biostate are important, right? Important information. So here the question is, initially I sent the biostate through the channel. After some time, the biostate no longer biostate, become highly corrupted. So the question is how to recover those biostates. So then I can show these 3 non-RU decomposition can be written in this way for the particular initial state. right? Which means, you know, this become the RU decomposition. For some, I mean, even globally is a non-RU, but for some states become RU. That's the kind of trick we perform here. So here, you know, that's the scheme. Okay, so here, you know, starting from this one, so this is the initial state, okay? So vacuum, we assume the quantum state, you know, environment initially is prepared in the vacuum. So here, this of course, you know, this putting them together we call quantum channel, right? So this is the total evolution, you know, of system plus environment here, right? Now we have a measurement here. We measure the environment. For example, we just measure we have a photon detection, you know. So this is a kind of parity measurement. So the result could be we get vacuum, means no photon here. We get even number of photons, or we get odd number of photons. So we have a three, you know, we have a, you know, each measurement, of course, we have outputs. But all outputs can be classified into three categories. 0, no photon, even number of photons, and odd number of photons. Depend on these three measurement outputs, right? Here. So each one, you know, for each one here, you know, which means we have three measurement operators, M1, M2, M3, right? So this for odd number of photons, this for vacuum, this for even number of photons. So for each of them, you know, we can perform one of three operations. Then we can always recover initial state. This is the message, you know. So here, you know, if we know, if a measurement, after measurement we got vacuum means no photon, right? Then we perform RC1. We can recover original state. If we get the output here, like you know, we get 3 photons. Perform RC2, recover original state. If we get even number of photons, you know, we have 20, for instance. Then we perform R3. In any way, we can always recover initial value state. So this is a kind of, you know, channel we show, you know, for some important initial state, we can always recover those kind of important states without assuming the channel has to be RU decomposition. Yeah, that's the kind of idea. So here, I just show you, go through here, you see this decomposition, so vacuum all state, that's it, yeah. Okay, so I'm not going to spend time on this one, so I just very quickly go through this one. So this is the new scheme, you know, basically worked out by Calvin Wang. I said he's a high school student here, I mean in the university. So the work actually, you know, we find out, I mentioned this one. So the last slide, right? We have a kind of recurring scheme, but only for some states, although they are important, like Bell state, right? But not for arbitrary state. Essentially, you have to think about, oh, I have to recover arbitrary state. You know, given a state here, I try to recover this state later. But we only perform measurement to recover some important state. Here, the work is we have to, you know, to generalize the measurement scheme. Here we use a weak measurement. You know, this is called POVM, positive operator value measure. So it's called POVM. Is the most general type of measurement. So we know, you know, in the quantum optics, quantum mechanics book, you know, the measurement typically discussed there is called von Neumann type measurement. It's called projection type measurement. So in that case, you have a very sharp, you know, result each time. You just decompose all possibilities by the projection operators. Here we talk about more generalized measurement, you know, satisfying this condition, you know. This is the only required condition. You know. Summing over all possible M, measurement operator, I got I, which means I cover all possibilities. Without asking, you know, if they're orthogonal, you know, mutually exclusive, we don't ask this kind of condition. So, initial state is rho, for instance, right? After measurement, this is state for the post-measurement state here. You know, this probability to get this one. So very similar to the von Neumann type environment, but much more general. So here you see this is just traditional von Neumann type, so I'm not going to work on that. So I think I will go very quickly. So the one example here, the weak environment, this is the weak environment here. You see this is state, right? A house state. If you, careless and just corrupted your state a little bit, so this one become this one. The coefficient here, 1 minus lambda, this is 1 plus, 1 minus delta, 1 plus delta, this one. Of course, two states are different. The question, how to recover this one? I recover this state from this one. By performing weak environment, we can do that. So very quickly, I will go through this one. So, the idea is I have this corrupted state. Then I have to add one more quantum qubit here. It's called a working qubit, right? So I perform, the rotation on this working qubit and put them together. Now I have two qubits. I perform C0 gate. After that, I perform another reverse operation on the working qubit. Altogether, this one is the final. Take this form. You can ignore the detail, but this one. So now you measure the working qubit, depend on the output. So if y is a 0W, then of course state, by properly choosing the parameter, you recover this original state. Of course, you could have this probability here, then you have to repeat the process, which means the weak environment here is not deterministic. So that's, our scheme here, this one, I only need to explain this one carefully. So our scheme is this one, you see. Here, we have a system environment. We have a unitary evolution, we have a decomposition here, and have measurement. Measurement now, before this is called, unitary matrix. We can perform a standard quantum operation. But if this one is not, so we cannot really use a quantum operation. We have to use this kind of weak environment. So that's the purpose. So here, I just show you this slide. So this is the final one. Okay? So this one is basically, starting from this initial state, right? Arbitrary state. So environment prepared into this state. So altogether we call the quantum channel. Okay. So now we measure the environment. Okay. We measure environment. For each measurement, the system here. So you see we have two tracks here. By measuring the environment, the system will collapse into one of component. You can call, some people call this is one like a quantum trajectory. You have many realizations, but for each output of the environment, then the system automatically is pushed into a particular state, represented by this one. But remember now, Kn is no longer unitary matrices, right? You cannot just like naively perform a reversal operation to recover the original state. That's impossible. So now the question is, the result here, you see, if K is invertible, is not invertible, then of course we can't do anything because this means the information gets lost completely. So here we don't require unitary, but we require the matrix is invertible. Invertible means the matrix has inverse, right? So if K is invertible, then we can have this one, perform this reversal measurement. This is a weak measurement. This is the difference from the original quantum operation proposed by Werner, because in that context, you have to assume the K here is unitary, but now it's just invertible. But the price we have to pay, we have to perform a weak measurement. So now, what's the overall consequence? First, original scheme is deterministic, right? Now, our process is no longer deterministic, which means you have some kind of a successful rate. Sometimes higher, sometimes lower. So you can suitably choose the decomposition, which you have many invertible matrices. Because as I said, the decomposition itself are not unique.